Good morning, students. This is Janaki, Associate Professor of Chapter Department. Was here to discuss about my lecture, Introduction Lecture 2 on electromagnetic field theory. So in this lecture, I was going to discuss about the core structure of electromagnetic field theory and a brief introduction on each and every unit. So let me start sharing my screen. So electromagnetic field theory introduction lecture 2 consists of a brief introduction on the entire course EMF called EMF. So in this, mainly the contents in my lecture, today's lecture is on introduction to EMF and a brief introduction on the 5 units called electrostatics. Unit 1 is electrostatics, Unit 2 is conductors, capacitance and dielectrics, Unit 3 is on magnetostatics, and Unit 4 is on force and magnetic fields, self and mutual inductances, time varying fields. And coming to the introduction to EMF, before going into the subject, we should know that the EMF is divided into 3 parts. Mainly it consists, it's split into 3 parts called electrostatics, magnetostatics, and electromagnetics. So a electromagnetic subject is a study of the effect of charges at rest and charges in motion. So coming to the special cases of the electromagnetics, which was discussed that it was into basically divided into 3 parts, electrostatic, magnetostatic, and electromagnetics. So the electrostatics is the study deals with the charges at rest. Magnetostatics, here we deal with the charges in steady motion, that means in DC currents. You know what is a DC current, right? So in the same way, what do you mean by electromagnetic? Electromagnetic is nothing but the charges in time varying motions, that is nothing but AC. Alternating currents. Coming to the fundamental concepts of the various fields which we are going to discuss in the electromagnetics are, we are going to go deal with the concepts of electric field intensity, which is coming into the concept of electrostatics, which is represented by E. And as also in depth in the next part, we'll be discussing a vector quantity. So usually the electric field intensity is having some direction. So that is why we call that this is a vector component. The electric field intensity usually represented with E bar, but here I'm going to represent for the simplicity only the scalar quantities. So it is taken as E. So and the units of electric field intensity E will be in terms of volt per meter. So, and the second quantity, important quantity, which we are going to discuss here is electric flux density, represented by D, and its units will be in terms of coulombs per meter square. And the third parameter is magnetic field intensity, which will be in terms of H, and its units are ampere per meters. And the next parameter is magnetic flux density, units are Tesla, or sometimes we call them as Webers per meter square too. And these are the basic parameters or basic field quantities which we are going to study in the concepts of electric statics as well as magnetostatics. And then, what is an electromagnetic wave? How these electric fields are getting transmitted? See, if you look into the picture here, there is a transmitter and there is a receiver. We all know that we are in the present globalization world, telephone, how we are going to use the telephone or the mobile phones. So the traveling waves, okay, the field waves are traveling from the tower which was installed at a far away from your location, and that tower receives the signals in terms of from the concept of transmitter receiver combination, and all the electromagnetic waves will be transferred to your device, and hence you can use a mobile or your connecting call like that. So here, see that here, the point here is what to be noted is when an event in one place has an effect on something that a different location, we talk about the events as being connected by a field. That field is your electromagnetic fields, subject on electromagnetic fields. So a field is spatial distribution of a quantity in general. It can be either scalar or a vector in nature. As I discussed earlier, it can be either a scalar quantity or a vector quantity. Then coming to the introduction or the contents of electrostatics, let us see the syllabus is designed in such a way that the electrostatic unit 1 consists of introduction to vector algebra, coordinate systems, Coulomb's law, where we are finding out electric field intensity due to line, surface, and volume charges. And here we also calculate work done on point charge, electric potential due to point charges, line charges, and volume charges. Also, we calculate potential gradient. And coming to the next law, very important law called as Maxwell's first equation or Gauss law. I think you're all aware of Coulomb's law and Gauss law to some extent in your earlier semesters. And here we go, like we use the laws and we find out the electric field intensity calculations and to some extent the potential calculations with the help of these two laws in this chapter. And the Gauss law and its several applications will be used to find out the magnetic flux density as well as magnetic field intensity E, which was discussed here in the last slide. So apart from this Coulomb's law and Gauss law, we also speak about a Laplace equation and Poisson's equations and how they have a significance in finding out the fields in the concepts of electrostatics. And also we also discuss in this particular chapter a few numerical problems on the several calculations, electric field calculations and potential calculations using the above two laws. And coming to the unit outcomes, here the students are able to determine electric field intensity potential using Coulomb's law and Gauss law and understand the Laplace Poisson's equation and their applications. Then what are unit outcomes? You would have also listened to my previous lecture. There I have given a brief introduction on unit outcomes. So every outcome-based education system needs a concept, few parameters as discussed earlier, like what is an OBE. So in this OBE, outcome-based education, we have the several concepts like objectives and outcomes. So there the outcomes of the entire subject has been discussed to you in the earlier lecture, but here, particularly to the outcome of this particular unit, the students will be able to know or to determine the field intensity and potentials using Coulomb's law and Gauss law, and also understand the concepts of Laplace and Poisson's equations and how to apply them in finding out the field intensity and potential calculations. And here, one of the topic in the first unit is introduction to vector algebra. So then what is a vector algebra? So vectors is nothing but a quantity which is having both direction and magnitude. Then unlike a vector, the controversy to the vector quantity is scalar. See, you know, from the picture you can see that the speed of the car is nothing but a scalar quantity. Okay, so what do you mean by scalar quantity? It is defined here. If you just look into the picture, the scalar is defined as a scalar is a quantity that is fully described by a magnitude only. It is described by just a single number. Some examples of scalar quantities include speed, volume, mass, and time. And here comes what is a vector. So in this picture, if you could see, weight is a vector quantity. Why weight is a vector quantity? Because it is having a particular direction in this meter. So then the vector is defined here as a vector is a quantity that has both magnitude and direction. Okay, please make sure that it has both magnitude and direction. Vector quantities are important in the study of motion. Some examples of vector quantities include force, velocity, acceleration, and momentum. Okay, so you know what is a force. Every one of us know what is a force. So if you just consider this particular Faraday's law, if you are aware of already Faraday's law, so particularly the thumb is indicating the force direction. So why only this direction? Because it is having some systematic procedure, some unique procedure, unique principle to follow. So always the force is indicated by thumb. So that the thumb is indicating the force direction. So it is having a particular direction. Okay, though it is having some magnitude, it also includes with the direction. So that is a vector quantity. So now in the other concept of your first unit, we are going to discuss about coordinate systems. Then what do you mean by coordinate systems? So if you just go look into the points, all those points, if I just simply summarize these points, usually the coordinate systems are of three types. Okay, if you want to describe the coordinate systems into three categories, like if you consider a line a single dimension, you call line is nothing but a single dimension. So there are single dimensional coordinate systems, and there are the planes where you have two-dimensional coordinate systems, and also you have a planes in terms of three-dimensional coordinate systems. So that means the entire coordinate systems can be categorized into single dimension, 2 dimension and 3 dimension. Here, so far you know what is a single dimension. Single dimension means which is varying in terms of x direction. And then what is 2 dimension? 2 dimension is nothing but, let us suppose, in terms of varying in terms of x and y direction, where x and y both are mutually perpendicular to each other. And coming to 3 dimension, you are already aware of a 3-dimensional coordinate system. If you were aware, so there you have a directions called x-axis, y-axis, and z-axis. So where all the 3 axes, all the 3 coordinates are mutually perpendicular to each other. What do you mean mutually perpendicular to each other? Which are varying with respect to 90 degrees from each of them axis, each of their axes. So likewise, now here in our subject, we are going to use, preferably we are going to use a 3-dimensional coordinate systems. So there in 3-dimensional coordinate systems, there are different types of 3-dimensional coordinate systems to be considered based on the assumptions. So now here, the first type of coordinate system is Cartesian coordinate systems, which is very much known to you all, nothing but called as rectangular coordinate systems. And the second type of coordinate systems is cylindrical coordinate systems. And the third type of coordinate systems is spherical coordinate system. So we will go in detail when we start the first unit, okay, in the lecture of the next lecture called first unit lecture. So but here to just summarize what is a Cartesian, what is a cylindrical, and what is a spherical system, so I'm going to discuss in the next slide. So what is a Cartesian system? Cartesian system, as I told you, it is having x-axis, y-axis, and z-axis. So if you see the picture, there is an x component, okay? X is equal to constant, okay? And that is nothing but parallel to yz plane. Here there is another plane called y is equal to constant, that means the parallel to xz plane. And here one more plane parallel to xy plane, or z is equal to constant. We can term either way. If you combine all these 3 planes together, then you can see a cuboid like this. You can see a cuboid in this pattern. So where you have x is equal to 0 plane, y is equal to 0 plane, z equal to 0 plane. So the ranges of x can be varied in a Cartesian system, or the limits of x can be from minus infinite to plus infinite, and the y can be from minus infinite to plus infinite, and z can be from minus infinite to plus infinite. So this is a brief introduction on what a Cartesian coordinate system representing of. And then comes the cylindrical system. So here the cylindrical system, again it is having, as it is one of the 3-dimensional coordinate system, it has a constant plane z which is parallel to xy, and it is also having another parameter called r and another parameter called phi. So here comes a new thing, new parameter to be considered as phi. So now here, if you see a cylindrical system is nothing but a basic thing, we can say cylindrical, cylinder like this. Okay, so how the cylinder is formed then? So that is important. So based on the value z is equal to constant plane and phi is equal to constant plane, if you consider together, along with, of course, r is equal to constant plane. That means if you consider a constant radius, if you consider a constant radius for a cylinder, and if that radius is moved towards along a direction of z direction with some particular coordinate, and if that radial parameter, if it rotates round with an angle phi, then you can say that a cylinder is formed. Okay, so that means the plane with r is equal to constant looks like this, and the plane with r is equal to constant, phi is equal to constant is in the second picture, and z is equal to constant is in the third picture. So together, if you consider all the 3 coordinates, the ranges of the variables, what are the variables here? The variables considered here are r, phi, and z. So usually r is a radial component which can be varied from 0 less than or equal to r less than or equal to infinite. And then what is the range of this phi, angle phi, which is usually called as plane angle. So this angle varies from 0 to 2 pi. 2 pi means 360 degrees. And whereas coming to z can be varied from minus infinite to plus infinite. That means the cylinder can be considered in the negative axis or in the positive direction too. So this is all about a few concepts of few brief introduction of cylindrical system, where we go in detail when we start with the unit. And next comes the spherical system. Then how do a sphere forms? Okay, so for considering or for understanding a spherical system, again, three variables are important or are to be known. So let the three variables are radius of sphere, okay, and then plane angle phi and cone angle. What is that? Cone angle theta. So here comes cone angle. So the new introduced angle here or the variable here is cone angle. So let us consider only the cone angle, means the entire angle made by this vertex. So the entire angle, if it is considered as 2 theta, let us consider half cone angle for our coordinate system. So that is nothing but theta, simply theta, not 2 theta, it is we have to consider theta. So how much should be the range of theta? If you see here theta, usually if it is entire angle, it is 2 theta, okay, 2 theta will be 2 pi. So theta will be 2 pi by 2. So that means pi, which is we are considering only half angle. And whereas earlier how we discussed in cylindrical system, similar way you have to consider the plane angle as 2 pi only. And the radius to be considered from 0 less than or equal to r less than or equal to infinite. So now with this assumption of cone with some particular unique radius, and if you just revolve the cone in all the possible directions of your plane, that means around around 10 degrees, and then tilted with another 10 degrees, again moving towards a 360 degrees 2 pi plane angle, and again like that if you just move on, so entire picture which will be resembling is a sphere. So this is how a sphere is looking. So the picture, the sphere of radius r with a center as origin. This is a picture of how it looks. So, and this is just a small information about spherical system. And coming to the next topic in the first unit is Coulomb's law. I think you're all aware of Coulomb's law. So what do you mean by Coulomb's law? So a scientist called Coulomb has stated that if you consider 2 point charges Q1 and Q2, as in picture Q1 and Q2, so and they are separated with some distance r, then the force experienced by the charges is directly proportional to the product of the two charges and inversely proportional to the square of the distance between them. So this is a statement given by the Coulomb. So with the basic concept or with the basic consideration of this statement, we are going to find out the particular force calculations in the next in detail in the chapter 1. And then once we know the force, we can find out the electric field intensity. Then what is the relation between the force and electric field intensity? So the amount of force experienced by a unit charge is nothing but called as electric field intensity, simply to be defined. So now if you consider a point charge, a positive charge Q1, and if you consider another charges Q2 at a particular location, so then definitely there is a force experienced by these two charges, which is given by the Coulomb's law. So F2 bar is the force experienced on the charge Q1. Okay, so now the electric field intensity is defined as amount of force experienced by this charge Q2. That means F2 bar by Q2 is your electric field intensity expression. And these are how the electric field lines look like. And now coming to here, if you consider a positive charge, always the electric field lines means electric field lines. Okay, field lines means electric field lines chart from positive charge, whereas the field lines stop on negative charge. And more charge means more field lines. That means if the charge is increasing, definitely the number of field lines also increases. And remember one thing, never the field lines cross each other. That means always the field lines move parallel or in another direction, but never they cut each other at any point. Okay, so that is a main property what you have to remember. And coming to field line spacing indicates field strength. That means if the field lines are nearer to each other, the field strength is more. And if the field lines are far away from each other, it indicates that the field strength is less. And this is the up to here, these are the just only a few basic components or basic definitions or some properties related to the first unit. And later on, we go in depth with the first unit, like as described the structure with the Gauss law, with the calculations of potentials, potential gradients, Laplace and Poisson's equation. So now coming to the second unit, so here the topics considered here are mainly this entire unit is again falling into the structure of electrostatics only. So where you have, we will be discussing here about conductors, capacitance and dielectrics. You know what is a conductor, okay, and you know how the capacitance is calculated and what is a dielectric. So all the known terms earlier only, but we will be discussing a little in depth because we have to know how to calculate capacitance, okay, in further to know the further, how we can say, calculations into real electrical engineering terms. You should know how to calculate. So as I told you in the last lecture, that EMF is just a backbone, like kind of support to all the electrical subjects. So now here, the conductors, how to calculate, what do you mean by conductors, how to calculate its capacitance based on the dielectric medium. You know, capacitance is basically a two plates. It consists of positive plate and negative plate. That means it is a positive charge and negative charge. So these two charges separated by some distance. Not only distance, here some medium is existing. So that medium is called as dielectric medium. Usually we call it as epsilon R. So now here the topics will be electric dipole, dipole moment, which has to be discussed. And then we will be discussing on the topics the potential, electric field intensity and torque due to electric dipole, behavior of conductors. That means if a conductor is existing, like what is the nature of what is the property of a conductor, what could be the property of insulator and how it behaves when it is a semiconductor. And also a few concept of boundary conditions. That means if you consider a boundary, what do you mean boundary conditions? That means the dielectric medium is the one which separates the boundary between the two regions. That means if I consider this particular part as a region or a boundary, okay, this is a boundary. Below this, if I say there is a medium of air, and above this there is a medium of some other material. So then the boundary is the one which is used to calculate how the medium or how the field intensity moves from this medium of A to the medium of another material. So what this boundary is helping us, how it is helping us. So to calculate the field intensity or to calculate the flux density or to calculate the potential at this boundary. So there are some formula, unique notations to be followed and which will be discussed in detail in the chapter. And next comes the capacitance and its calculations in parallel plate, spherical and coaxial capacitors. You know already if there are two parallel plate capacitor, that means if you have a capacitor, single capacitor and another capacitor connected in parallel, you know what is a combination or what is the equivalent capacitance of parallel plate capacitors. In similar way, of course, you know like how they are connected in if series, then what is the equivalent capacitance also, you know. So in the similar way, the capacitance not only will be in series or in parallel, but also some capacitance are usually in spherical, also maybe in terms of coaxial. So let us discuss in detail like what are the capacitance calculations for those structures too. And also, and next, the next topic comes with energy stored, energy density in static electric field. And comes the next topic is current density. Okay, what do you mean by current density? We'll be defining here and we'll go, there are two types of current densities, conduction and convection current densities, and also Ohm's law in point form, which gives us or which helps us to find out the equation of continuity, and we will go with some numerical problems of this particular chapter. So here comes again the outcomes, what the student will gain from this unit. So the student will be able to or are able to evaluate the capacitance and energy stored in electrostatics, understand the concepts of electric dipole, conduction, convection current densities, and energy density. So then, as I told you, this entire topic is related to capacitance. Then what is capacitance? You know, capacitance is nothing but charge per the potential. That means amount of charge stored to gain a unit potential. You can say simply, so C is equal to Q by V, you know already. So C is equal to Q by V. So the units of capacitance usually are farads, coulomb per volt, we can say otherwise. And what is the energy stored? So here, like in the first chapter, I told you there are various types of charge distributions. That means the charge is not simply a line charge. It can be a surface charge or it can be a volume charge. So based on the type of charge distribution, we will be using a dimensional coordinates. I told you already. So there, if it is a line charge, the energy stored will be integral, half integral rho L dl, dl into volts or joules, you can say. Okay, and the surface charge is half integral rho s ds. The volume charge is half integral rho v dv. And comes this up to here, these are just only covering a few points on the second unit, whereas we go in depth with the calculations of spherical as well as other capacitor connections. And next comes the third unit. So what the third unit consists of? The third unit consists of static magnetic fields, which is having consisting with the main basic laws with the Biot-Savart's law, which will be useful in finding out magnetic field intensity due to several arrangements like straight, circular, solenoid, current, wire, etc. And also we will be discussing about Maxwell's second equation, nothing but called as Ampere's circuital law, and its applications in finding out magnetic flux density as well as magnetic field intensity with their relation. So magnetic field intensity due to infinite sheet of current is another parameter we'll be calculating, and then long current carrying filament too. So point form of Ampere's circuital law, Maxwell's third equation, and we will discuss some numerical problems in this particular chapter. So as I told you already, magnetostatics is nothing but the study related with uh, static magnetics. That means in a stationary, or simply we can say DC currents. So if you have a current carrying conductor, if you consider current carrying conductor according to right hand thumb rule, which you know earlier, so if you consider current carrying conductor, then the curl fingers indicates the magnetic field lines. Okay, based on this concept, we can say this is a DC current carrying conductor. So if you consider DC current carrying conductor, it is having the magnetic field circulating around, surrounding it, and the direction of curl fingers. So here, so that is nothing but your magnetic field. Okay, so now what are the outcomes here? The outcomes will be the students can apply the concepts of magnetic field intensity using Biot-Savart's law and Ampere's law. Also, magnetic field intensity due to infinite sheet of current and long filament current in different loops can be calculated. And then what is how magnetic field? I told you already, like to develop a stationary current, we require a magnet. So let us consider the North Pole and South Pole. That means the magnetic field moves always in a particular direction from north to south externally and south to north internally, which you know already. So in the same way, so let us say that this is a bar magnet, how the field looks like. And if you take a like poles, what happens? Like poles repel each other. It's one of the property which you know already studied in your earlier physics. Non-like poles attract each other. So if you consider a horseshoe magnet, this is how it looks. So here the field lines based on the property, it circulates like this. So and this is how the Earth's magnetic field looks like from north to south. Okay, and now this is one more structure where we need to concentrate about solenoid. So solenoid is one type of like current. If you consider a hollow cylinder, and if you wound a current carrying wire on it or a conductor on it, then definitely the current carrying conductor, as I told you, based on the direction of the current passing into the coil or into the solenoid, it acts as a north pole or south pole. That is how the field moves as per the thumb rule I told you, or modified thumb rule we can say. And again, this is one more picture representing how the two poles are existing. If two south poles are there, how the magnetic fields are repelling, and if two unlike poles are, how it is attracting. And it is a similar picture of earlier picture. So now I told you direction of magnetic field. How we get direction of magnetic field? If you consider a electric current holding a conductor like this, and thumb is indicating the direction of the current, and the curl fingers indicates the rotating magnetic field. So if in the same way, like if you rotate the electric current, like, okay, if you consider solenoid, I told, no, solenoid I told. So if you consider a solenoid, if you rotate the electric current, then the curl fingers indicate the current direction, the thumb indicates the field direction, where this is called as modified right hand thumb rule, which is applied for solenoid. But whereas for a single current carrying conductor, straight current carrying conductor, right hand thumb rule is applied, and for a solenoid, modified right hand thumb rule is applied. Like here, this is one more representation of how the field is looking like. So usually we say the current in two directions, in forward direction and backward, or current into the board and current outwards board. If you consider the current into the board, then the magnetic field is like this. And if you consider the current outwards about, the magnetic field is like this, which is represented in the figure, middle figure like this. And then what are the properties of magnetic field? We already discussed that always a field, the magnetic lines start from North Pole and ends at South Pole of the magnetic, and they are crowded at poles when the magnetic field is strongest and the lines do not intersect each other. Each line is continuous closed curve passing to the next magnet. And next, the topic on force. Till now we have studied what is an electric field, how the electric field moves, how it is developed from the concept of Coulomb's law, and what are the several calculations related to electrostatics, including capacitance calculations. And then we have gone with the third unit in terms of magnetostatics, where the magnetic field intensity will be calculated, flux density will be calculated. And also I'm saying that there is a force. What is the force now here? So force in magnetic fields, how it gets into. So to get the force in magnetic fields, usually we have a concept called Lorentz force equation, which will be discussed in depth in the unit. So, and also force on current element or a straight long current carrying conductor in magnetic field, and the force between two straight and parallel current conductors will be discussed over here. And also we discuss magnetic dipole moment and how its torque is calculated. And then the concept of inductance here comes. So how the inductance is calculated? You know what is an inductance already. So using the Newman's formula, we can find out the inductance calculations, mutual inductance calculations, and also we determine the self-inductance of solenoid and toroid too. So if you consider two circuits, what is the mutual inductance between the two circuits? Circuit like straight long wire and square loop, also calculated in this particular chapter. So, and also we find out what is the energy stored in magnetic field, and to some extent few numerical problems will be discussed on all the concepts in this chapter. And then what are the unit outcomes? So here the outcomes are to determine the force, torque, current carrying element in the magnetic field. And also students will be able to determine magnetic forces, torque produced by current carrying elements in the magnetic field. Then what is the Lorentz force equation? So here the force equation is a combination of both electric force and magnetic force, simply I can say. So I told you already, electric field intensity is nothing but force per unit charge. That means you can simply say electric force is equal to Q into E bar, where it is having a direction. So a notation called vector has come here. And in a similar way, what is a magnetic force? If you consider a charge moving with some velocity in a magnetic field, that is your magnetic force, which is known to you already. So if you combine the concepts of both electric force and magnetic force together, we call that as a Lorentz force equation. Simply I can say F bar is equal to Q into E bar plus Q into V bar cross V bar. What is this cross? In vector, you know, cross is nothing but indicating if you have two vectors, to get the mutual, if the resultant is in the mutual perpendicular direction, then you use a cross product. So here, in the figure, if you see this is a velocity and this is a magnetic field and flux density, then its mutual direction is given by F bar. Okay, mutual perpendicular. That is the reason we say that here V bar cross B bar is used. And magnetic torque. So the moment of the force or torque about a specified point is defined as a vector product of the moment R bar and force F bar. So usually torque is also a vector component again. So torque is also having a particular direction. So we have to say that we have to use a cross product simply for cut to the point. And if we go in detail in the concepts of magnetic torque, what is this vector, how the direction, why we are using cross product, why we are using dot product, why the resultant is again a vector. So this I will discuss in the brief when I go into the subject in detail. Now I told you there is a concept of calculation of inductance. So what is the inductance means? Again, there are two types of inductances here. If you consider a single coil, single circuit, the flux developed with due to its own circuit is called a self flux, which you know already. So the self inductance can be calculated as L is equal to N phi by I. That means the amount of flux, okay, developed due to its own current. So that is your self flux and hence self inductance. And then what is this toroid? See, I told you already, we have discussed in the starting of this unit, solenoid is there. Okay, what is a solenoid? A hollow cylinder is there, and on it a wire is current carrying wire is wounded, and hence which is developing a magnetic field. Here comes toroid. So now the solenoid, if you consider the solenoid as a straight bar, if you just join the edges of the two straight bars, this looks like a toroid, a circular. So toroid, and on this toroid, if you wound a wire, if you wound a wire on this toroid, so that will be inductance. We need to find out an arrangement of the conductor of such arrangement of a toroid. What is its inductance? And this is solenoid, what I told you already. And coming to the last unit, which is time varying fields. So far, electrostatics is over, magnetostatics is over. But now the third category of electromagnetic field theory is time varying fields. That means electromagnetics. So in this chapter, we are going to discuss of several Maxwell's equations in their integral form as well as derivative forms. Then what is a Maxwell's fourth equation we'll be discussing? Maxwell's fourth equation is nothing but, which is very well known to you all, Faraday's law of electromagnetic induction. So modified Maxwell's equations for time varying fields, and also a concept on Poynting theorem, Poynting vector and its significance. So here the outcomes are to understand a time varying fields, Faraday's laws of electromagnetic induction, illustrate Maxwell's equation in different forms, Poynting vector and Poynting theorem. So these are the this is just a simple table of different Maxwell's equations in their differential form as well as integral form and their significance. So if you consider this as a del cross E bar minus rho v by dou t, and integral form is integral E bar dot dl bar, which is nothing but Faraday's law. And similar way, the other law is Ampere's circuital law, which we have discussed already, Gauss law, and no isolation magnetic charges for del dot B bar is equal to 0. So this is a table, and we'll discuss in detail about all these equations. And this is your Faraday's law. So Faraday's law means, you know, in the machines we'll be using that for both for a generator as well as for a motor, you say EMF is developed. So what is the EMF developed? Minus N d phi by dt. So how it is developed? Based on Maxwell's fourth equation. So if you see here in this picture, see this north and south pole is there, Faraday's law of electromagnetic induction, representing a current carrying wire is there. If a magnet moves inside and outside like this, what you can say, EMF is developed. And that EMF developed is alternating in nature. That EMF developed is in alternating nature. And this is the Poynting vector, depends on E bar and B bar. So simply we can say S bar is equal to E bar cross B bar. And this is how the Poynting vector direction is moving. So these are the few parameters I'm highlighting in this particular topic, but later when we go in depth, we'll be discussing in detail. Thank you. If any queries, you can just contact me with my mail ID, which was given to you in the earlier class. Thank you all.